So we've talked for a bit here about right triangles, and you may be wondering why. Why do we spend all our time talking about right triangles and trigonometry? Why have you heard about this stuff? The short answer is it's because right triangles are everywhere. Even things that don't look like they are right triangles are right triangles. Here's just three examples. The first here is a regular pentagon. And I don't think I'm going to have to convince you too hard that you can break this up into right triangles any number of different ways. Like if I would do, say, maybe start in the center and go to each corner. Now, these aren't right triangles yet, but if I do this, now they are, right? Go straight perpendicular to each side, and now I've got 10 right triangles. So we can analyze this five-sided shape by treating it as 10 right triangles. Anytime you've gone outside and seen your shadow, you may have done an experiment with this in a science or another math class. Guess what? We're talking right triangles. That's how we can figure out how far away the sun is, how far away the moon is, how big things are that we're not measuring directly. Right triangles everywhere. Over here is an example of a building. This is one of my favorite buildings ever. It's in Abu Dhabi, and it's called the Capitol Gate. And it really is built to look like it's leaning, or like it shouldn't be able to stand up under its own weight, because this end of the building is not on top of anything. It's a gorgeous looking building, but it's all triangles. Just like we divided up this pentagon, anything that looks even curvy, if you zoom in enough on it, looks flat. And if it looks like it's flat, you can make triangles out of it. Analyze those triangles, and that's how you make a building like this stand up. So why does it matter? It's because these triangles are everywhere. Now, just some examples. So let's look at one. If you want to look at more, then you can continue on in the video. We'll just do a couple more like this. But here is a triangle where we want to be able to find the area, but we're missing an important measurement. I hope you remember from previous courses that the area of a triangle is 1/2 the base times the height, where the base is one of the sides, and then the height is the perpendicular distance. Notice here in this triangle, we don't have that. We don't know what h is in this particular triangle. But using our right triangle trigonometry, we can figure out how long that h is. So it goes a little bit like this. Let's take a look at this triangle here. I've got, let's see, a hypotenuse and an opposite side and an angle. So opposite and hypotenuse is sine. So the sine of 70 degrees is the opposite length, which is the height of the triangle, divided by the hypotenuse length. So the height of the triangle is 9 inches times the sine of 70 degrees. Now, I just want to get a sense here of how much that is. So quick check, make sure I'm in degrees. Oh, I wasn't. Yeah, so switch over to degrees. Okay, so the height here is about 8.457. Now, here's the thing. Do not round this number. Do not do any rounding until the very final step. So over here in my calculation, I'm actually going to leave it written just like this and put it all into the calculator at once. So area of the triangle now, 1/2 times the base, which is going to be the 7 inches on the bottom, times the height, which I'm going to leave written as 9 inches times the sine of 70 degrees. Throw all that into the calculator at once. Here we go. So actually, let's take what we already have typed here and just type in some more. So 1/2 times the 7 times 9 sine 70 degrees is 29.6 square inches. So, moral of this story. Right triangles matter because you can make anything into right triangles, including triangles that aren't right. You can just drop an altitude, it's called, and now you have a right triangle. Now, if you would like to do a couple more examples like this, continue on with this video. If you're comfortable that you've got the idea about how right triangles matter so much, you can move on to the practice. Okay, another example here. In this case, we're actually going to have to drop our altitude outside the triangle. That's okay. The same procedures still work. So if I'm looking at the overall area, I want a half times a base length times the height. That's what I don't have yet. We need to do a little bit of thinking here. Like I've got this diagonal length is 8. So of this red right triangle over here, that 8 would be the hypotenuse. I don't know this length here, but we can figure out this angle because together these two angles make up 180 degrees. So subtract the 105, that means this angle here has got to be 75 degrees. So opposite hypotenuse, the sine of 75 degrees is this h that I don't know, divided by this diagonal length, which is that 8 centimeters, multiply the 8 over. Okay, so that's the height I'm after. 75 degrees. Throw all this into the calculator machine. So half times 5 times 8 sine 75 degrees. About 19.3 square centimeters. There you go. Notice again, didn't do any rounding until the final step. That's the only place my rounding should occur. Okay, do a quick pause here. I want you to try this one, see how you do. Okay, gotta use this bottom 15 as my base. Need to figure out what the height is. So drop in that altitude. So it's again opposite hypotenuse. The sine of that 69 degrees is h over 15, opposite over hypotenuse. So multiply the 15 over. Okay, throw all that in the calculator. About 105.0 if I'm rounding to the nearest tenth, which is what I'm going to do. So that is right about 105.0 square inches for this area. So, I mean, be a little bit impressed here. That right triangle trick, dropping in that altitude, enabled us to find the area of a triangle that, without it, we couldn't. And then lastly, once again, I'd like you to do a quick pause, unpause when you're ready to give things a check. So for this one, I think the easiest way, based on how it's drawn, is to set up my height over here. So then, I'm going to be having area as a half. Base would be the side of the triangle perpendicular to the height. All right, and now over here, 125. So take 180 minus 125. Is that 55? Okay, then. So again, it's opposite hypotenuse. So the sine of that 55 degrees equals the height I don't know over that 8-mile hypotenuse. Multiply the 8 over. And what do we end up with? Let's give it a check. Was it 55 degrees? Yeah. Okay, I'm going to call that 29.5 square miles. Okay, thus endeth our video here. So the big takeaway, just using area as an example of how you can take something that isn't a right triangle and use right triangles to help you work with it.